Welcome back, everyone. I finally had time to come back to Talos and try to do some simulations to see whether the design of the control card was okay or not. And unsurprisingly, it was not okay at all. There were several errors, several mistakes, which you find immediately when you simulate something. That's why simulations are so nice. I'm going to show you first what the errors are, not in detail, but just give you an idea of what is going wrong. What you see here is basically the circuit that you saw last time. There are some more chips, but that's basically to help visualize what's going on. So there are several sets of buffers with LED bars, like this one here, which visualizes the output of the instruction memory. I put a dip switch on top, which allows me to sort of simulate what the output of the instruction memory is, an opcode or an immediate value. I can just set the bit switches here to the dip switches here to visualize that and simulate with a certain value. You see more of this buffer plus LED bar combinations here. So for instance, this one here visualizes the content of this decoded instruction register. This one here, the same for this register, and so on and so forth. We have the immediate register here, which can drive the internal bus high and or the internal bus low, or the internal bus low, and another buffer plus LED bar set to visualize its contents, and one more here to visualize the contents of the instruction register. So that's what you're seeing extra, the dip switches and the LED bars with respective buffers. I also made one alteration here. The function is the same, but I decided to use two of the NAND gates that I had spare on this 7400 chip over here. I decided to use them to invert the read and the write strobes instead of the available inverters from the 7414. They are still inverted. It's exactly the same as before functionally. I just moved them from this chip to this chip, and the reason is I'm already thinking about placing and routing the board, and the more modular I can make things, the better. So now I have a circuit here that can be placed separately from this circuit here, and another one over there that is more or less separate as well. They're never completely separate, but I'm trying to make things more modular, so I give myself some more freedom during placement and routing. Now let's see what's wrong in this board. Let's run some simulations. I have here the key signals that I need to simulate the thing. This is the N halt, which is basically the halt signal, which is active low, therefore the N for negated, the N reset, and the clock. So we can, I'm recording this in pretty high resolution in the hope that you can still read what is in here. I can make it a little bit bigger, but if I make it too much bigger, then I can't see anymore what's going on, like the dip switches. One tick is smaller. It's difficult to find it's too big. Yeah, I cannot do much better than this. So I hope you can see it, but I will narrate it anyway. So the first thing we have to do, you see here the current value of reset and halt is 0, meaning the system is halting and resetting. So let's bring it out of reset, bring it out of a halt. And now we can click on the clock. Every time I click here, it's a transition of the clock signal. Rising edge, a falling edge, then a rising edge, then a falling edge, and so on and so forth. So if we click on the rising edge once, there we go. Nothing will change here because remember, there is a circuit that manages the halt and reset. Manages the halt. And when you start up the system, that circuit operates as if it were coming out of a halt. So things don't happen immediately. So now that the clock is high, nothing happened here still. But, and that's the first error, this is the clock signal that goes into the program counter. And the program counter is wired to always count. So the moment I hit the clock here, the program counter which came out of reset pointing to address 0, is now pointing to address 1. But as you can see down here, the program counter output enable is still inactive. In other words, the program counter is not outputting its value to the instruction memory. So it's already counted to address 1 without addressing the memory. So you already lost address 1. The system as it is here will never point to address 1. Then let's click on the clock again. So we have a high to low transition, or a falling edge. Now it's a falling edge. Now finally, the program counter output enable, which comes from the decoded instruction words stored in these 4 registers, it is now active. So now we are pointing to memory. And the program counter is still pointing at address 1. But we still didn't latch anything from memory. We are pointing to memory at address 1. Let's say there is opcode 1 in address 1. Now let's click the clock again. So now we have a low to high transition again, a rising edge of the clock. That means that the program counter has counted again. So now we are pointing at address 2. Let's say that we have opcode 7 in address 2, which is a address register 1 increment, or AR1++. So we can see in this LED bar now that that's what is on the output of the instruction memory, but nothing has been latched still. Now on the falling edge of the clock, now we latch the value from the instruction memory into the IR. This is the IR, and we can visualize the value latched here on this LED bar. So finally that has happened. Now we start from address 2. That's where we fetch the first instruction. That's wrong, but anyway. And the pipeline still has a no op because it's still not filled. It takes a few cycles to fill the pipeline. So when the clock goes high, we will point to the next address in instruction memory. And let's say there is an AR2++ in there, opcode 8. And now, let's say we will halt the processor now. No instruction has been executed. The AR1++ is already in the IR, so it has to be executed at some point before or after the halt. But let's halt it now. Halt is 0, and now the halt will be managed by, the timing will be managed by this little circuit here. So on the falling edge of the clock, normally the opcode 8 should go into the IR, and the opcode 7 that is here should then be executed. So the clock goes down, opcode 8 is loaded, opcode 7 is indeed now in this decoded instruction registers, and you can see that, and I'll zoom in to show you. You can see that on this light green line, which is a 1, and it goes into port B4, and it will come out in port A4, which is here, and it is AR1 count enable. So it is in the execution stage, but look, the output enables are all 1 now, and they are active low. So these buffers here have just been tri-stated as part of the halting process. So the AR1++ is in the execution stage, but it's not being executed because the buffers are tri-stated, and therefore all values here are pulled low and everything is inactive. We don't see the AR1 CE that we should be seeing, even though it is there right before the buffer in this light green line, coming into B4 and coming out of A4. Now, this instruction then, if everything is correct, has to be given half a cycle to execute after we come out of the halt stage. For as long as we are in the halt state, I can click on the clock and nothing will happen, you see? Nothing's changing. Except that the program counter is also counting. And that's the other error. I don't manage the clock line during the reset state. During the halt state. And I should pull that clock out. Otherwise, the program counter will count and the system will skip several instructions in instruction memory that it will never see again, and then that's not good. But let's pretend that that problem is not there, because there is still another problem, and the other problem is that the AR1++ that is in here will never execute. And to show that to you, let's say instruction memory, the program counter is now pointing at another AR1++. So we have an AR1++ here, we have an AR2++ here in the instruction register, and the first AR1++ is still here in the execution stage but not being executed. So now I come out of the halt. Now this AR1 should be executed before the AR2 goes in here and the next AR1 goes into the IR. Is that what will happen? Let's see. Clock goes high. Clock, these are still tri-stated. AR1++, the first one, is still not being executed. Clock goes low. Oh, now they are not tri-stated anymore. You see the NOEs are dark green. I actually see a value already being set. There is an LED shining here. So now they are not tri-stated. But what is being executed now? Well, let's have a look. This LED corresponds to this light green line, which is the AR2 count enable. So now we are executing the AR2++. And the original AR1++ that was here has fallen off the tracks. The next AR1++ is now in the IR, and the AR2++ is being executed. So we skipped an instruction. That's not right. That's the problem. You see, so 3 problems we have here. We skip address 0 and 1 in instruction memory. The program counter counts through during a halt. And the way the halt is managed lets some instructions, at least one, fall through the cracks and never be executed. Even when you come out of the halt, the system doesn't remember that it still had to execute that instruction. It just forgets that it was there. It sort of purges it off the pipeline without being executed. That's also a problem. So we have to tackle all these 3 problems with a new version of the circuit, of the control card. And this is the new version. There are a few changes here, nothing dramatic. I will walk you through all of them. The first thing I did is I'm always clocking the immediate register now. I'm not withdrawing the clock from it, because I noticed that it doesn't matter. Even if you allow it to clock, what's important is that it have the correct immediate value when a load immediate instruction is here in this decoded instruction registers. I labeled them now DIR3 down to DIR0, and these are the decoding memories DM3 down to DM0. So I always clock the immediate register. Let me show you now with a little animation how this works to convince you that it does work even if you clock this register all the time, so long as you manage the NOP generator correctly to make sure that the pipeline is in sync. Let's have a look at that animation. So like before, this is what comes out of instruction memory. It can be either an opcode or an immediate value, and the data path is split in 2, one path for the immediate values, another path for the opcodes. The DIRs are the decoded instruction registers, those 4 registers that hold the output of the decoding memories. In other words, the 32-bit decoded instruction word is here. You translate the opcode into the decoded instruction word through the memories. That's what this means, just like before. The difference is now that the IM will be latching at every value that comes out of the instruction memory. Everything that comes out, even if it's an opcode, will be latched here as well. So what you have to make sure is that the timing is correct. So when this value is an actual immediate, next to it in the decoded instruction registers, we will have the decoded instruction for a load immediate, an LDI. Well, I'm not using this mnemonic, but you know what I mean. The contents of the decoded instruction registers have to correspond to a load immediate when next to them we have an actual immediate in the immediate register. Let's see if that's what happens. This is the convention that we were using before. It's the same. Red is a load immediate opcode, green is another opcode, yellow is the actual immediate value, and black is a no op or 00, X00. So we come out of a reset state, everything is black. everything is a 0, 0. And then the first opcode comes from instruction memory and it gets loaded in the instruction register. Let's say it's another instruction, it's not a load immediate. So this isn't a load immediate. It also gets latched by the immediate register, you see, because it's being clocked all the time. The line is dotted because that latching means nothing, it's just garbage. But it does happen, it is latched. And now the program counter increments and we have the next opcode, and this time it's a load immediate opcode represented in red. And the same opcode gets loaded in the immediate register as well. It's garbage, but it gets loaded. And the previous opcode goes down to the decoded instruction registers. Now, because this is a load immediate, now the circuit has to make sure that when the next thing comes out of instruction memory, it goes to the immediate register, because that next byte is the actual immediate value that follows a load immediate opcode. And instead of loading that immediate here on the instruction register, which would be terrible, because then it would get interpreted as an opcode and it would add rubbish to the execution. You would be executing an instruction that isn't an instruction, it's an immediate value. So instead of latching it in the IR as well, like before, the no-op generator kicks in and latches a no-op in the instruction register. And then when the next cycle comes, that no-op will go down. And that's what we have to make sure. Right now, the load immediate is here, right next to its immediate value, you see? So that's the timing we want. We want that when an actual immediate value is here, then next to it in the decoded instruction registers, we will have the actual load immediate. And then in the next cycle, the no-op comes down, and then you no longer have an immediate value here. Now you have just an opcode, but it doesn't matter because now we have a no-op here on the other side. And that's how you keep the synchronization. That's how it works. All right, so that hopefully has convinced you. So that was the first change. This is just a little oscilloscope. This here is an oscilloscope. It's not part of the circuit. It's just a tool that Logisim Evolution gives you, allows you to monitor the signals that you plug in there. And these are the signals that I've plugged in there. I can even zoom in a little more. So I'll be monitoring these 4 signals. And this is basically, it's called an oscilloscope, but it works as a logic analyzer. So you see how the transitions are happening for the signals that you're monitoring. Another change I made, I have separated clock from system clock. Clock is now managed. I withdraw the clock during the halt condition. And that's the signal that goes to the other cards of the CPU. System clock is the output of the oscillator. This one is not managed because it's what comes out of the oscillator. It's always there. And I have a negated version for this as well, an N system clock. As you can see here, system clock just goes through an inverter. If I open this up, system clock goes into an inverter and comes out as N sys clock. That's all there is to it. So sys clock and N sys clock are just the outputs of the oscillator. One is the inverted version of the other, so they are out of phase by 180 degrees. And then we have the N reset and the N halt. We already had them before. The way the halt is now managed is slightly different. This is what happens here. And this is the circuit that manages the NOP generator that we've seen last time. And it's basically the same circuit as last time, except that I added a little bit more delay. I added some more of the AND gates here as delay because they've become available, since I needed a separate AND chip to deal with the halt. Let me show you what is happening here in a gate representation. That's the gate representation. Sorry, you can't see me anymore. But this is basically what manages the output enable of the transceiver that forms part of the NOP generator. It's just like before, but before we didn't have these 2 extra gates here for delay. Now they've become available, so I added more gate delay. Remember, you cannot use this file here in a simulation it would be incorrect because these modules I'm using, for instance, the set and the reset are active high, while in the chips, the 7474 here and here and here, they are active low. But I made things here in order to conform with the chips. So I'm just using Logisim Evolution here because it has already the icons with the symbols that I need, but you should not use this file, which is in the repo, in the repository on GitHub. It is there, but you should not use it for simulation because it would have the opposite behavior of the desired one, since the convention for what is active high, what is active low are not being obeyed here. Now, this is new. This is the little circuit that manages the halt circuitry. And as you can see, instead of one flip-flop, it now has 2 flip-flops and 4 AND gates. Let's walk through this so everything becomes clear. I am no longer taking the program counter output enable from the decoded instruction word. And the reason for this is that if I take the program counter output enable from here, then it will be in sync with the tri-stating of this transceiver. So if I tri-state this transceiver, the program counter output enable disappears and the program counter is disabled. So there is a timing enforced between this NOE and the PCOE if I let the PCOE go through the transceiver. And that adds a constraint in the timing I have to manage. So instead of doing that, I'm just taking the PCOE out of the reset signal, which is what is shown here in gates. So what is the PCOE? Well, the PCOE is basically the negated reset signal. So when reset is active, in other words, it's 0, then that 0 goes here, passes through 2 AND gates. That's just to buffer the signal, to add some oomph to it. And then it becomes the PC output enable. So when reset is 0 or active, PCOE is 0 or inactive. So only when Talos is in a reset state does the program counter output enable becomes disabled, and the address bus of the instruction memory now is tri-stated, and it becomes available for a DMA device like an I/O controller to upload new code into instruction memory. But the program counter is not disabled during a halt state, because the halt state is such that you're not going to update the instruction memory. You're still running the same code. You just have to halt while executing that code to give DMA or direct memory access to the I/O controller, but you're not going to reset the instruction memory. So if you do want to load the new code in the instruction memory, then you need to put Talos in a reset state. That's what this means. So we can forget now the upper part. What is left? We are left with this now. So let's see what happens here. During the reset state, this line is active. Let's see where it goes. It goes down here into the reset line of the flip-flop. So during the reset state, this flip-flop will be reset and the value Q will be 0. So 0 will go into this AND gate and mask the system clock negative away, so we don't get AND clock, which is the clock for the control card. So the clock for the control card will be withheld when we are in a reset state, because that reset resets the output Q of the flip-flop, which becomes a 0, and whatever you end with a 0 is 0, so you get nothing on the other side. Now let's continue to follow this reset line. It comes here and goes into the set input of the other flip-flop. So when the system is in reset, this flip-flop is set, meaning that Q will be 1, and that Q becomes the negated output enable, which is what goes into these transceivers here. There you have it, the NOEs. And the NOEs are active low, so when they are 1, these transceivers are tri-stated. So the transceivers are tri-stated during a reset, which is what you get here. Now, that's the reset state. Now, when we are not in a reset state, we've come out of reset. Let's look at the normal operation of this thing. That's the halt signal. When the system is not halting, this will be a 1. Therefore, 1 on the D input when it's clocked, it will go to the Q output, which will be 1, and end with 1 is whatever was on the other side of the end, which is the negated system clock. Therefore, we will get the end clock, and the control board will operate. It will be clocked. Things will be latched into the instruction register, into the decoded instruction registers, and so on and so forth. Moreover, if this is 1, Q is 1, and therefore the complementary output will be 0. So D will be 0, and once it's clocked, Q will be 0, but Q is the NOE, which is active low. So the transceivers here will be enabled, and we will get the control signals from the decoded instruction word going to the rest of the CPU. Now, if this Q is 0, then the complementary output is 1, it goes into the end, and whatever you end with 1 is the other input of the end, which is system clock. And therefore, the rest of the CPU, including the other cards, including the program counter, will get the clock. All right, so now we saw what happens when we are not in a halt state. What happens when we do halt? When we do halt, this will go to 0. And then in the next rising edge of the system clock, which is the clock input of the flip-flop, on the next rising edge, the 0 will be passed to the output and will mask away end clock. So we lose end clock on the rising edge of the system clock, which is what I try to show here. If this is system clock with rising and falling edges, and the halt happens somewhere here, then on the next rising edge, this edge of the system clock, we will disable end clock. That's the first thing that happens. And remember, end clock happens on the falling edge. So we disable end clock on the rising edge to make sure that we are not disabling it while it's happening, which can lead to race conditions and logical errors. So we disable the end clock half a cycle before it was supposed to tick. So at this point, on this rising edge here, the 0 of end halt is in Q, and we disabled end clock, but the complementary output will now be 1. So D, the input of the next flip-flop, will be 1. And it will be latched on the output on the clock. But what clock is it now? It's now the inverted sys clock, which means the falling edge of sys clock. So on this falling edge of sys clock, this, which was 1, goes to the output and therefore disables the transceivers, these transceivers here that put out the control bits. So on the following edge, we disable the transceivers, which is exactly what we want to do. That's the correct timing. Now, it may take too long to explain to you again why this is the correct timing, but if you take these files, which are all in the repository, and you study them, you understand it. Now, in addition to disabling the transceivers, because Q will be 1, the complementary output will be 0, which goes into an AND gate. Therefore, if one input of the AND is a 0, the other input gets masked away and we lose the clock. And therefore, the rest of the CPU, the other cards, will not get the clock, and the program counter will not get the clock. And therefore, the program counter will not count while we are in a halt state. And all of this will happen on the falling edge of the system clock, which is half a cycle before the next rising edge, which is when the program counter would count. So we disable it half a cycle before it would happen, and not at the same time that it is happening, because otherwise we get a race condition. That's not a good thing either. So this is the circuit that you will see now on the main simulation file, and this is the timing. It's what it tries to accomplish. For the outgoing and incoming mail flags, I didn't change anything. I didn't test it either at this point, and that's why I will need your help this time again, but I will talk about that at the end of the video. So if we go back to Alto, the circuit I just explained to you is this, plus the little booster for the PCOE, which was this part here on top. So this here is this here. It's what it does. All right, and since I had extra gates on the top here, and I already talked about it, I added more delay for the same reasons we discussed last time. I also pulled up some of the outputs that are not produced by transceivers, like the outgoing mail flag and the incoming mail flag are produced by a flip-flop chip, not a transceiver. So I pulled it up to boost that signal a little bit. I did the same thing for the read and write strobes here and here, because they are produced by a 7400 and not a transceiver. So I pull it up to boost it a little bit. This pulling up slows down the signal. The rise time and the fall time will be longer, because this resistor in combination with the parasitic capacitance of the line creates a little low pass RC filter, which filters away the higher frequency harmonics, and therefore the rise and fall times are now slower. But in a system like this that will run at 1 or maybe a few megahertz, that's not a problem at all. It's even advantageous, because those higher frequency harmonics are the harmonics that tend to get reflected and compromise signal integrity. So by pulling it up, I'm adding a subtle low pass filter that removes the reflections. It's a very minor effect, but anyway. All right, let's run a simulation now to see if this is working fine. We have our little logic analyzer in there. Let me zoom in so you can see better. So we will be observing these 5 signals here: the system clock, the managed clock, the managed inverted clock, the output enable of the transceivers, and the halt signal. And we control only 3 of them, these 3, the system clock, the reset, and the halt, because clock and unclock are now managed. They are the result of the operation of this little circuit here. So they are the result of the simulation, not the input to the simulation. So let's go into this little finger here, which is my simulation tool to set the signals. Let's see what happens now. I begin in a reset state, and reset is dark green, which means it's a 0 and it's active low. So the PCOE is also a 0, as you see in dark green here. So the program counter is not pointing to an instruction memory, and therefore the output of instruction memory in here is irrelevant. It's just garbage there. That buzz is basically floating. So let's bring the system out of a halt and out of a reset. The moment I bring it out of a reset, the program counter output enable is now light green, which means it's 1 and it's active. So now the program counter is addressing instruction memory. Which address? Well, 0, because we just come out of a reset, so all registers are zeroed. So the program counter contains 0 and it's pointing at address 0 of instruction memory. Let's say that we have opcode 7 in address 0. So now we have something here on this line. The output of instruction memory is now 7, which again is the opcode for AR1++. So I'll be alternating between AR1++ and AR2++ because they are easy to recognize here in the decoding stage, just like we did before. So now we have AR1++ here, nothing in the IR. It's still zeroed because we just came out of a reset. Nothing in the execution stage. Not only because these registers contain 0, but because these transceivers here are tri-stated. NOE is still high, as you see in light green. So they are tri-stated, the outputs are floating, and the control signals are pulled down by these pull-down resistors here. So they are all zeroed, which means that everything else is tri-stated. All the other buses are tri-stated except for the output of the program counter. So now we are going to hit the clock for the first time. System clock, that is. System clock goes high. Let me zoom in. So system clock is high, but the managed clock is still low, so the program counter didn't count. It didn't increment. And clock is still low, so nothing has been latched here in the control card. NOE is still high, meaning the transceivers down here, these transceivers are disabled because NOE, as you can see here and here, they are still high in light green. So essentially, nothing happened yet. We are coming out of a reset state. Let's see everything again. Now system clock will go low. That's a falling edge now. Okay, now something happened. Now IR has latched the output of instruction memory, the contents of address 0, which is opcode 7, which is AR1++. AR1++ is now in the IR, as we can see here. The transceivers, as you can see now, they are all enabled because NOE is dark green. The transceivers are enabled. You can also see it here. NOE has a falling transition. See a falling edge of NOE here in the logic analyzer. NOE has come down. The transceivers are enabled, but all control signals are still 0. Why? Well, because the pipeline is not filled yet. This is a 3-stage pipeline. It takes a couple of cycles for something to get to the execution stage. So let's now hit system clock again. So now we have the first transition of the managed clock, which will tick the program counter. The program counter will now increment and will point to address 1. Let's say that address 1 contains opcode 8, which is an AR2++. So at this point we have AR2++ here, AR1++ here, and an NOP or a NOP, an OOP here. These are the 3 stages. AR2++ here in the fetch stage, AR1++ in the decode stage, and a NOP in the execution stage. That's basically what this means. If we now click on the system clock again, now IR has latched the AR2++, so we now have AR2++ in the decoding stage, and the AR1++ should now be here in the execution stage. Is it? Well, there is an LED lit up here, so there is something. If we follow the light green, there we go, AR1 count enable. So this is indeed the AR1++ that is now in the execution stage being executed. Now, because we had a tick of, we didn't have yet a tick of the clock, we still have the same opcode coming out of instruction memory. But if I now click on sysclock, 2 things will happen. We have a positive transition of the clock here. So program counter is now incremented. So it's pointing to address 2. Let's say that address 2 contains opcode 7, which is AR1++. And also the result of the AR1++ that is in the execution stage, in other words, the first AR1++, now it has been latched because the rest of the CPU latches on the positive transition of the clock. And we had a positive transition of the clock here, the managed clock. So AR1++, the first one, is in the bag. It has been executed, its result has been latched. And AR2++ is still in the decoding stage. So now if we hit system clock again, now the IR will fetch the second AR1++, the next one, which is now here, or here in the IR, as you can see on this LED bar. And now AR2++ is in the execution stage, which it is. Look at this LED here, it's lit up. It's the light green line, which is AR2 count enable. So now we have the first AR2++ in the execution stage. It has just entered the execution stage. Its result has not been latched yet, because it will only be latched in the next rising edge of the clock when everything gets latched. So now it's being executed while the AR1++ is in the decoding stage. Now, at this point, let's halt the system. Halt is now 0. See, it has come down and it's active low. So the system should enter a halt state now, managed by this little circuit here to manage the timing, just as we discussed. So on the rising edge of system clock, now system clock has been ticked. Let's look at the managed clock. It has had a rising edge. So the AR2++ here has completed execution. Even though halt went low, the system still allowed the clock to tick one more time in order to put the results of the AR2++ here in the bag. It's now in the bag. It has been completed before we actually entered the halt state, even though the halt signal has already gone active, has already gone low. We still allowed for one more transition of the clock in order to put this result in the bag. Otherwise it would be lost. We don't want that. So the result is now in the bag. The clock has been properly managed, and now we still let me see. The PC also increments, so this will go to the next address. Let's say it's opcode 8. So now we have opcode 8 in there, opcode 7 in here, which is a AR1++, which is still being decoded, and the AR2++ that is in the execution stage has been completed. The result has been latched. If I now keep hitting the system clock, nothing happens, you see? Nothing will happen. The system is now tri-stated. The NOEs are now 1. As you can see here, the NOE is high. So these buffers are tri-stated. All the control signals are now low. So the address bus is tri-stated. The data bus is tri-stated. DMA and DMA devices, I/O controllers can now just use system memory themselves. And nothing's happening in the CPU. Although I'm hitting the system clock, the CPU has just stopped, and it stopped in a state in which the program counter keeps pointing at the address that contains opcode 8. The previously fetched opcode 7 is in the decoding stage, and nothing's being executed. The AR2++ that was there has been completed. It's now out of the picture. The result is bagged, it's latched, and the system is now just waiting. So let's now come out of reset. The clock is low, system clock is low, and now reset goes high or inactive. How does the system come out of reset? Now, IR has an AR1++, which is in there, but we still need a transition of the end clock for these registers to fetch the decoded version of the AR1++. They still contain the previous instruction, which was AR2++, which is now executed. It's out of the picture. Yeah, that's the right way to interpret this. So there is a shadow of the AR2++ here because the registers are still holding the previous instruction that's already executed. It's already out of the picture. And the IR register is holding the AR1++ instruction, whose decoded results are not yet latched by DIR. So now we go for a positive transition of system clock. We just came out of reset. And let's go. Positive transition of the system clock. What happens? Well, these transceivers are still disabled. Nothing happened there. Still don't have a positive edge on the clock, so the program counter is not pointing anywhere else. Now system clock goes down. Oh, now something happened. Now IR has fetched opcode 8, and the decoded instruction registers have fetched what was there before, the decoded version of the AR1++ that was previously in the IR. So now we should have here AR1 count enable, and indeed there it is. That's what we get there. So we have the next instruction now in the execution stage. But that result will only be latched on the next positive transition of the system clock, which is now. Now this AR1++ has been executed, and we had a where is the clock here? We had a positive edge on the clock, and so on and so forth. So you get the picture. Now instructions are not getting lost in the pipeline anymore. Now I will run a few more tests, but I'm making all these files now available in the repository, including this, which is not a simulation file, it's just a diagram for your understanding, and including this, which is the updated instruction set spreadsheet. The main change is I removed the program counter output enable signal because it's now managed directly. It comes out of the reset. So there is a space there that I call free. And so there is this bit which is never set. And we now have a 31-bit instruction word effectively, and the 32nd bit is free. I may use it at some point in the future. I may or not. I don't know yet. But the PCOE is now managed directly by the circuitry. It doesn't come out of the decoding memories anymore. That's the basic difference. So all the files are there now. So I would like to again ask for your help, because simulating this way requires a lot of attention, takes a lot of time, and I would feel a lot more confident about proceeding to a PCB design if at least some of you run the simulation yourselves, try different test conditions, like different moments to halt. Do you halt the CPU on the system clock being low or on the system clock being high? Do you unhalt the CPU when the system clock is low and the system clock is high? Does it work the same way? You know, all these combinations that would be nice if you guys would test as well alongside with me, so we sort of come to a place of comfort in which we can proceed. So if you do that, even if you don't find any errors, please let me know that you run some tests yourself, and me describe very briefly in words what tests you run, so at least I know that somebody else has checked for this as well. And if you run the test and you find an error, then really please let me know in the comments below what the error was that you found, so I can try to reproduce the test here on my side and reproduce the error, and we can fix it before we go to a PCB. So that's the first help I would like to ask you guys to help me with, is running tests of the halt circuitry here. The other thing I'd like to ask your help for, or your feedback on, is the following. I'm thinking of using two PLAs to implement the circuitry. Some PLAs that are certainly programmable from, you know, the usual programming devices like the TL866, and I had a look at the list of supported devices, and they all support the ATFs22 chips, which are the chips I would use here. So if you're going to use a TL866 to program the memories, the decoding memories, which will be flash memories, then you might as well just and you have to use it in order to program the PLA here. Then you might as well use it to program a couple of ATF22 devices to implement all this. Because then it allows me to make changes to this circuit even after the board is completed. I don't need to spin another PCB if I find an error in this circuit. I can just reprogram the PLAs. Just like I can reprogram this PLA if I change the instruction decoding some way. Notice that I'm using a different block here. It's the same functionality, it's the same PLA. Logisim has two PLAs. One is where is it? One is here, and there is another one somewhere else. And I was using the other one, but the other one doesn't work in the simulation. It looks nice, but it doesn't work. So I moved to the alternative, and this one here does work. If you open it up, you don't see the ANDs and NOR gates anymore like you did in the other one, but you can still program the product terms directly. Like if we have 8 input bits, this combination of values will lead to a positive output. And this basically means that if this PLA sees opcodes 1, 2, 3, 4, 5, or 6, which correspond to the load immediate instructions, then it will activate the NOP generator and put the next value from instruction memory into the immediate register, just like we saw. So the question I would like to ask you is the following. Should we implement this in 74 series logic like it is here now? Or should we just use one or two PLAs to implement this as well and make the PCB design simpler, a lot less traces, and preserve flexibility for changing the design afterwards? The only reason to continue to use 74 series logic is that I think the ATF22 is out of stock at Mauser right now. It will be back in stock on the 1st of May next year. I didn't check DigiKey and the other many suppliers, so maybe the ATF22s are still available. I have a bunch at home, more than enough for myself. And I probably, if some of you still want to build your own Talos before those components become available from Mouser, I can send you a couple of these pre-programmed chips as well. So one of you wanted to bring Talos to a vintage computer festival. If that requires the chips to be available before they are available at Mouser, I can help you. I can send you the chips. So let me know what you prefer. Should we stick to 74 series logic, which are available, or should we move to DIP through-hole packaged ATF22 devices, which look just like 74 series logic, except that you can program the product terms and the flip-flops inside? Should we move to that in order to preserve flexibility, not only to allow us to fix errors, but to allow final users of this mini computer to change its logic as well? I mean, they will be able to change the instruction encoding because this PLA will be programmable, so maybe they can change the how to logic as well and the reset logic in a limited way, but still allowing for some changes to customize it for themselves. So let me know what you prefer. Should we do this in one or two, probably two ATF22 programmable PLAs, or should we stick to 74 series logic? So let me know in the comments below. So in the meantime, I'll just be waiting for a few days until you guys, if you want to do that, run some simulations yourselves and give me some feedback. And then towards the end of the month of November 2022, which is when I'm recording this video, or beginning of December 2022, then I will go to the PCB board design and we will have a decision about whether the circuit is correct and whether to use 74 series logic or programmable PLAs. So I'll be counting on you and waiting for your feedback. In the meantime, take care and I'll see you next time. Oh, wait, there is one more thing we didn't simulate. It's not really needed for you to follow the series to watch this part now, but for completeness, I wanted to simulate that the logic that activates the no-op generator, which is this, where is that logic? It's here, it's this logic here. I want to show that it still works even though we are clocking the IM register all the time, the immediate register all the time. So let's run another simulation here. So let's bring the system out of reset, out of a halt state. The PCOE is immediately active. We are pointing at address 0 in the instruction memory. So let's put a normal instruction. Let's put again an AR1++ in there. An instruction that does not entail loading an immediate value. And then we hit the clock. There it is. Then we hit the clock down again, and now we have that instruction is latched by the IR, and it has entered the instruction execution, the instruction decoding stage. And if we hit system clock again, we have a rising edge of the clock, so the program counter is incremented. We are pointing out to address 1 in instruction memory, which I will say contains a load immediate. Opcode 1 is a load immediate. This opcode 1 loads an immediate into register A high. That's what it does. So let's see what will happen if we continue execution. So system clock goes low. So that opcode is now latched into the IR, as we see here. On the execution stage, we are now executing AR1++. AR1's account enable is active, as you see there. So AR1++ in here is in the execution stage, and the load immediate is here in the decoding stage, and it's addressing now the decoding memories. If the circuit is working correctly, now I will have a rising edge of the system clock, which leads to a rising edge of the managed clock, and therefore we will be pointing to the next addressing memory, which will be the immediate. So let's say the immediate is just FF, or 255. And it's, as you can see there, the immediate register is still loading the opcode of the load immediate that is in the IR, because it's being clocked all the time. But on the next cycle, we should have the IR get a no op, and this immediate value here go to the IMM here, which we will see here on this LED bar. So now system clock goes low and we have a transition of N clock. So now look at what happened. We have the no-op generator kicking in, and we have a no-op here in the instruction register. It's all zeros now. You see? What's coming out of the transceiver is all ones because it's the immediate value, but what has actually been latched is the previous value that was there, which was being generated by the pull-down resistors here, because this transceiver was tri-stated. I forgot to point that out, but if you go back in the video, you will see that this line will have been light green just before I clicked the clock. So we had a no-op. We have a no-op latched in the IR, which we can see here in this LED bar. Nothing is lit, so everything is zero, and that's the opcode for a no-op. Everything is zero. All right, and we have the immediate value there in the immediate register. And what is in the execution stage? Well, let's have a look. We have A high load enable, which is exactly what we expect to have on the A high receives the immediate value. If we go back and look at the decoded bits, we have A high load enable 1, and that's what we get, A high load enable 1. What else have we got? We have the immediate high output enable 1. Let's go back to the instruction decoding spreadsheet. Let's continue to follow this line. There we go. We have immediate high output enable 1. That's correct. That's this bit here. Now we can even go further and see what is actually happening. This is the internal bus high, and it should be driven by the contents of IMM. Is this what's happening? Well, lo and behold, it is what's happening. Look at this line here, which is the output enable. It's dark green, which means that it's 0, and it's active low. So this is enabled, and that's why we see these light green lines here in the internal bus high. The internal bus low has blue lines, which means that they are floating. They are undefined. And that's because this transceiver is tri-stated. Its output enable has light green line, so that's 1, and it's active low, so it's tri-stated. So the internal bus high is now carrying 255, which is the immediate here in the immediate register. And the general purpose register A high has its load enable active. So A high will acquire the contents of the internal bus high on the next positive transition of CLK, of the clock, which will happen now. Boom. In that transition, A high has acquired the value in the internal bus high, which was 255, which came from the instruction memory in the form of an immediate. And now, since we had a positive transition of the clock, program counter will now point to the next instruction. So let me clear this, and I'll make the next instruction opcode 7. When the clock goes down again, then the no-op will come to the execution stage. The value of the load immediate is now latched. It was latched on this transition of the clock that I just hit. The same transition that incremented the program counter has latched the value of the internal bus high into the A high register. And on the negative edge of the clock, the no-op will go to the execution stage. Now we have the no-op here. Opcode 7 is now in the IR, as you can see on the LED bar here. On the execution stage, we have a no-op. And yes, we have an opcode in the immediate register instead of a register, or instead of an immediate value. But it doesn't matter because there is a no-op here. It's not doing anything with that immediate value. It's rubbish. It's just there. It's not going to change anything. So yeah, it works. The whole thing works even if we clock the immediate register all the time, so long as we make sure that whenever the immediate register is actually holding an immediate value, we have the decoded load immediate instruction here, as we had, as I've just shown you. All right, this is it now. Thanks for watching. Remember to give me that help to run some simulations if you guys feel like it would really be helpful. I'm not saying this just to encourage you to participate. No, I would really appreciate it if you guys run some simulations of, especially of the halting circuit, different conditions, and let me know in both cases if you are successful and didn't find any error, and if you did find an error, I would like to hear from you in both cases, and to give me feedback on whether you prefer that I stick to 74 logic for this part of the circuit or use two small little programmable PLAs that would give us a lot more flexibility and make the board design easier. Let me know. Right, thanks. Take care, and I'll see you next time.